What we're going to be looking at here is first order separable differential equations. Now we know what an equation is. We've studied them since S1. It's where we've got a link between two variables where one has a dependence upon the other. Typically, we'd write x and y, although obviously if we have different applications of it, we may use different letters. So for example, degrees Celsius and Fahrenheit, we'd use C and F, kind of natural instinct for that. What we're going to look at here is when we have some sort of differential within the equation that we have to work with. Now, one thing we have to understand is there's some terminology that comes into play that we have to make sure that we know the difference between. When it comes to working with a first order differential equation, it's an equation where dy by dx is the highest derivative present, and this is what we're going to be using to solve and get some sort of equation from to get rid of the derivative. Now, two things that we need to know here. We've heard of the words order and power. What we have to remember is the difference between them when it comes to applying them to our equation here. So what we have to remember is that order refers to the order of the highest derivative, i.e. what is the highest derivative we are taking. So this one here, dy by dx, this would be order 1 because it is the first derivative of the equation. The second term that we have to make sure that we know is power. Now, power is the degree of the highest power of the highest differential of the equation. And this can be different to the order. So essentially what degree means is the highest power to which we are taking. If we were to look at an equation, a quadratic, the highest degree within a quadratic is x squared. So the highest degree is 2. The highest power of x in a quadratic is 2. However, here we're going to focus on the derivative segment and the differential of it. Now, a couple of examples to show. This first one here, dy by dx equals x plus 4. Now this one here, the highest derivative is dy by dx. That means the order of it is 1, so it's a first order differential equation. In the degree, the highest power of the dy by dx, not the highest derivative, but the highest power associated with it, is 1. You know, this is dy by dx, and if you could imagine it being in a bracket, that will be a bracket with a 1 power outside of it. So the degree again is equal to 1. Now this one here, focus on the derivative segment again, dy by dx. It's the first derivative, which means that the order of this equation is 1. Now my degree, we've said, is the highest power associated with the derivative. Now we have an x squared here, so natural instinct to look at that and say that the degree is 2. However, because it's a differential equation and we're focusing on that derivative part, what we focus on is the dy by dx. Now, similar to the first one, the highest power associated with it is 1, so the degree of this one is still degree 1, despite there being an x squared here. Now, if we look at this third example here, again, similarly to the first two, the highest order derivative we have here is 1, so first derivative. So my order is 1. However, look at what's associated with it in terms of the dy by dx being in a bracket to a power 2. So I'm squaring the derivative of the dy by dx, which means that my degree is now no longer 1, my degree is actually 2, because it's going to be the highest power associated with the differential of our equation. Now, if we were to look at this one here, again focus on the order first. Well, the order is the highest derivative that comes into play. Now for this one, I've got a second order derivative. I'm taking the second derivative as my highest, so my order is 2. And then when we think of degree, instinctively, you'd look at d2y by dx squared and say, right, it's degree 2. However, d2y by dx squared, remember, tells you it's the second derivative, not power. So degree refers to the power of it, and the power of this highest derivative is 1. So what that means is the overall degree of this differential equation is 1, because it's associated, remember, with the highest power rather than the highest derivative. So this shows we can get different orders and degrees of a differential equation. We have to just pay attention as to how we refer to it, depending upon what part of the differential equation we're looking at. Now in this video, what I'm going to do is I'm going to focus on equations with separable variables. So what this means is if we can write an equation that takes the form f of y times dy by dx equals g of x, what we're able to do is separate the functions based on the variables and use this to help us to integrate the equation. So what I could do is I could have f of y dy by dx, take dx of that equal g of x dx on the right hand side. Now if I were to look at this, I could cancel out these dx's and I'd have f of y dy equals g of x dx. So I've got everything with a dependence upon y on one side, everything with a dependence upon x on the other side. What I can then do is integrate both sides with respect to their set variables and I'd get an equation. Now, key thing to remember is that this doesn't lead to just one solution. This leads to a family of functions represented by changing the constant of integration. Remember, we always have to include that when we integrate a function. This is what's called the general solution. Now, if I were to give you a set of initial conditions, say x and y, so a set coordinate maybe, and I was to then substitute these in, at that point I'd be able to find out the constant of integration and get a specific answer. This is what's called the particular solution, because it's a solution particular to that information you are given in the question. So remember the difference. General solution includes a general constant of integration. Particular solution refers to one set function within the family of solutions that the general solution refers to. But the overall set of steps to handle them is the same. The only extra thing is for the particular solution, we just do a bit of substitution afterwards. Let's imagine I give you this equation here. dy by dx equals 1 over 2x minus 1. And I say to you that I want you to find the general solution to this differential equation. Well, the first thing I'm going to do is separate it. So I've got all my x dependence on one side and all my y dependence upon the other. So if I were to do that, what I'd then be able to write is that dy equals dx over 2x minus 1. Now that I've got that, what I'm then able to do is say, right, so if that's the case, then I know the integral of dy equals the integral of dx over 2x minus 1. So if I integrate both sides, what I'm going to do is get a solution that satisfies both sides of that equation. So the integral of dy is just equal to y. Integral of dx over 2x minus 1, well, that would take the form of a logarithm, ln of 2x minus 1. But I have to account for the fact that if I were to take the derivative of this, I'd do 1 over 2x minus 1 times the derivative in here, which is 2. So to account for that, I have to have a half in the front, and then I'd have my plus c at the end of that. Now, we've got it written in this format. However, what I'm able to do is actually combine this, so I have just one generic term on this side. So what I can do in order to do that is if I write my c in the format of ln a, where a is just another constant, because I know it's just a generic constant, I can have it in whatever format that I want to suit the scenario that I'm in. If I have it written in this term here, ln of a, I can rewrite my right hand side as a half ln of 2x minus 1 plus ln of a. Now if I've got that, what I'm then able to do is take this power up using the rules of logarithms and make it ln of 2x minus 1 to the power of a half, then plus my ln of a, and I can then combine it all to then be able to write that y equals ln of a times the square root of 2x minus 1. So I can combine it all together into one standard format there, and what I can then do is if I were given initial conditions for this one, I'd substitute them in at that point so that I could find out what the constant a is, and I can get a particular solution. So there's my general solution to that equation there. So let's imagine I'm now going to give you another one. So dy by dx equals 1 minus 2y. But what I'm going to do is I want you to find the particular solution after finding the general solution in part A with an initial condition of x equal to 1 and y equal to 1. So when you get one like this, the first thing you should always think about doing is separating all the y's onto one side and all the x's onto the other. So if I were to do that and take this through here, what I'm going to do is I'm actually going to divide through by 1 minus 2y. If I were to take the y over, the 2y over, I'd end up with dy take away 2y, which would mean I'd then have a separate term with a y in it, but no associated dy. So what I'm going to do is divide by the entirety here. So for part A, I'd actually take this and rewrite it as dy over 1 minus 2y equals dx. It's a little trick to remember there for that. If you've got something of this form, take the entire thing over, because everything has to be associated with the dy in order for the integral to work out properly. What I can then do is just integrate both sides of this, so I know it'll be the integral here of those, and then after I've done that, I'll get my general solution. I can then get my particular solution based on the initial conditions. So if I were to integrate both sides of that, I'd get negative a half ln of 1 minus 2y equals x plus c. So what I'm going to do here is I'm going to take the half up as a power here, so use that rule of working with logarithms, but having the negative here would make it 1 over the 1 minus 2y, and I want it to be as easy as I can. So what I'm actually going to do is take the negative and multiply it across to this side. So what I'll end up with is ln of 1 minus 2y to the power of a half equals negative x minus c. Now what we want ideally is to have something y equals as a solution and then put our initial conditions in. So what I'm going to do is to get rid of the ln, I'm going to shift over to here and it becomes an exponential. So I'll then have the square root of 1 minus 2y equals e to the negative x minus c. Now this bit here on this right hand side, remember I can write that as e to the minus x times e to the minus c. Now e to the minus c is just a constant, so actually take this and write it in a much simpler format of a e to the minus x. So I've got square root of 1 minus 2y equals ae to the minus x. What I now have to do is get rid of the part so I get y equals, then substitute in my initial condition. So if I square both sides, I end up getting 1 minus 2y equals ae to the minus x squared. Well, again, we don't know what a is, so a squared, I'm just going to keep calling it a. It's a generic constant of integration. And I then get e to the minus 2x. I've then got minus 2y here, so if I switch that over and then move the a e to the minus 2x across here, I'll get rid of the negative. So I'll then be able to say that 2y equals 1 minus a e to the negative 2x. And then what I can do is divide through by 2. If I then rewrite this right hand side though, what I can have is 1 minus a over e to the 2x. Combine it into one fraction, and what I'll get is e to the 2x minus a over e to the 2x. Divide through by 2, and I'll know that y equals e to the 2x minus a over 2 e to the 2x. So now I've got x equal to 1, y equal to 1, substitute them into here. So from that, I can tell you that 1 equals e to the power of 2, take away a over 2e to the power of 2. Multiply through by 2e to the power of 2. What I'll end up getting is that e to the power of 2 minus a equals 2e to the power of 2. What I'll then do is take the a across and then bring back the 2e to the power of 2 here. And if I do that, what I'll end up getting is that a equals negative e to the power of 2. So now that I've got that, substitute that back into this equation here, and I can get my particular solution for those initial conditions. Y equals e to the 2x minus e to the 2, but it's minus, minus, so that becomes a plus, over 2e to the 2x. So there's my particular solution for those initial conditions. So it is a little bit of work, but we have to make sure that if we are given those initial conditions, we substitute them in at the correct point to get rid of that constant of integration. And like I say, a lot of the time, combine the constant like this because it's just a generic one that can take any format we want.